Hi, I'm Paula King, and Seattle Friends of Fission welcomes all of you to our talk on the Natrium Project in Wyoming. So Friends of Fission has been bringing experts to the public in Puget Sound for about 5 years. We've been bringing people to talk about nuclear power. And several of us decided that nuclear power to deal with global warming, and we need to dispel disinformation and just lack of information among people. So tonight, we're really pleased to have Mark Werner talk to us about the Natrium Project. Mark's a mechanical engineer who develops and leads engineering teams that design advanced reactor concepts focused on impacting future energy markets. So Mark's worked in plant layout and design, reactor system and equipment design, reactor core design, and fuel design in his past positions. Mark has worked for TerraPower, which is a local organization most of you probably have heard of, for the last 10 years, and previous to that worked on reactor designs for the U.S. Navy's nuclear fleet at Knowles Atomic Power Laboratory in upstate New York. So Mark has a master's degree in mechanical engineering from Union College and a bachelor's degree in mechanical engineering from Drexel University.
Well, I appreciate the opportunity to come and talk to this group about the Natrium Project. It's a project that I'm personally very excited to be a part of, and I know everyone at TerraPower is really excited about seeing developed. And I appreciate the intro. I don't have to talk about myself now. I am the Deputy Director of Engineering for the Natrium Project at TerraPower. I've been working on this project since its inception a couple of years ago. Natrium as a product is a TerraPower and General Electric Hitachi developed technology. And as Paula said, TerraPower is a local company. We're located in Bellevue. So I'll talk about Natrium today and give a little bit of an overview about TerraPower. We'll go through the technology. We'll talk a little bit about the project. We'll talk a little bit about the safety strategy and then the licensing approach. And then we'll open the floor up for questions about any of those aspects. TerraPower was really funded to solve kind of a energy problem at the global level. Our founding fathers really identified energy relation to quality of life. And you kind of can see on the plot to the right, a relationship between the Human Development Index and electricity use per capita. And so our founding fathers looked at this and said, a large part of the world population is kind of at a very low Human Development Index. And so in order to increase their quality of life, we need to increase the available energy or electricity to those populations. But how do we do that responsibly without impacting the environment negatively? When you look at the areas of the world with high populations that need improvements, you see places like China and India. But also what you don't see here is also Africa, which is also a growing area that needs improvement. So how can we supply a lot more energy without running out of resources and without seriously damaging the environment? And so they went off and thought about this for a while and really came up with this concept of a traveling wave reactor, which we'll talk about in a little bit. They came across the idea of this traveling wave reactor, which wasn't new, but was kind of more theory than engineering solution. Traveling wave reactor kind of is an extension of a breeder reactor. They have some advantages. They have a long-term sustainability at the world scale from a fuel utilization standpoint. They can reduce fuel cycle costs with respect to both mining and the enrichment costs, and they kind of enhance your front-end proliferation. The downsides of a breeder program is that there's a high cost to reprocessing, and there's the reprocessing also increases some proliferation concerns. But with a breeding reactor, you do get a lot of advantages from the coolant type, and the coolant type is a sodium-based coolant. Sodium-based coolant reactors have low pressure, so they have inherently safe reactor because of that. They have high thermal efficiency. The coolant is metal, so you're able to conduct heat out very well. And they operate at a high temperature, so there's quite a bit of market for high quality heat as an output. There are some disadvantages to this coolant type, material challenges, and some chemical reactivities, which we'll talk about later. So we kind of focused in on these breeder reactors, but we really wanted to take the advantages and not have any of the disadvantages. So we kind of conceptualized this TWR as a breed and burn reactor. And so what is the breed and burn concept? Well, it avoids reprocessing by basically taking the U-238, which is very abundant in natural uranium, and putting it in the reactor core such that it captures neutrons that are being emitted from the fission reaction, and that U-238 breeds into plutonium U-239, and then that U-239 becomes the fuel, which we then burn. This is best kind of graphically shown on the right. If you think about a green branch, if you're able to ignite one end of that green branch and have a burning region, that burning region actually dries out the green branch. And now that dried out green branch is actually burnable. So then your burning region can move into that dried region and burn. And as it moves into that dried region and burns, it is actually drying out the next region. And so this kind of traveling wave, if you will, of breeding and then burning the fuel is what the traveling wave reactor is based on. And so we went off and looked at this technology for a while and figured out how to implement it using a sodium fast reactor core and reactor systems. And we do that through shuffling the fuel throughout the core throughout its life, maintaining some regions of the core that are breeding up this U-239, and some regions of the core are burning that U-239 as a fuel. A number of years ago, we had developed this product and we're looking to deploy it as a demonstration project in China. China still is very interested in deploying nuclear power. They are trying to solve the energy issues that they have domestically over there. Due to some government regulations that got passed, we were no longer able to work in China. Then kind of turned our focus internally at our domestic market and figured out how we can rework the TWR technology into a domestically deployable product that has some benefit to the US energy market, and the US energy market has needs as well. Around this time, a lot of states and utilities were developing targets for carbon reduction in their energy mix. And so we saw this as a really great opportunity to develop an attractive nuclear product that we can get in front of utilities and deploy domestically. So that was the origin of the Natrium product. So going back about 3 years now, TerraPower reached out and started working with GE Hitachi, which is a company based in Wilmington, North Carolina. GEH, as I'll refer to them going forward, has had a history of developing nuclear reactor technology and deploying it both locally and globally. They have been working on advanced reactors as well. So TerraPower and GH formed a development agreement and co-developed the Natrium product. And we really kind of started over from scratch, trying to take the best elements of the traveling wave reactor and GEH's past reactor designs, but really focusing on the future energy markets and trying to design the technology to be very cost competitive, simple. We really wanted to design the product to have rapid constructability because we know that being able to deploy this technology quickly is important. Current nuclear reactors have an issue with staffing levels. They have a lot of staff that costs a lot of money to operate. So we looked at trying to reduce the required staffing level by being very conscious of staffing during design efforts. And ultimately, we were able to operate at pretty high temperatures. And so we're actually able to gain a higher net thermal efficiency of our reactor. And this helps with the economic impact that we're able to make with this reactor technology. One of the key things we noticed right away is that most of the utilities we talked about, renewables was on their energy mix. We didn't want to beat renewables. We like renewables. We know they're not the answer to everything, but we wanted to basically join with renewables. So instead of creating a competing product, we wanted to create a product that would integrate with renewables. And so we were able to do this by developing a reactor technology that implemented thermal storage or energy storage. And by integrating energy storage, we're actually able to integrate with renewables. And we all know that renewables through certain parts of the day can generate quite a bit of electricity, but during other parts of the day, don't generate a lot of electricity at all. By integrating energy storage into our product, we're able to kind of create energy throughout the day constantly, but store it up when renewables are generating electricity and then put it on the grid when they are not. So we call this load following or price following, and it is, we think, a very competitive advantage to our product. So the Natrium product is sized to be 345 megawatt electric nominal, but because of this energy storage concept, we're able to flex the electricity generation up to 400 megawatt electric for up to 5 hours at a time. And this is using this energy storage system, which I'll talk about later. So we came up with this concept a couple years ago. We started marketing it to utilities, and then along came the Advanced Reactor Demonstration Program. This is a congressionally backed program really focused on trying to get the U.S. nuclear industry back as a global leader in developing technology. So Congress decided to fund 2 reactor demonstration projects at a very aggressive level, and then a number of kind of R&D projects below that. So we put in a proposal with a really solid partner group, and we won it. And this program is really set out to demonstrate the ability to design, license, construct, and start up and operate this Natrium reactor. So the program covers all parts of that cycle. And we see it as a real opportunity to build the supply chain for these sodium fast reactors in the US. And then obviously we are interested in deploying this reactor technology because we see it as a key way to lower emissions by really deploying a fleet of Natrium reactors. This demonstration program will get us our first unit. And then once we're able kind of to demonstrate our ability to design and operate one Natrium reactor, we feel like there's quite a market out there to deploy more. And then obviously this program develops new jobs, both locally here in the Seattle area from a design standpoint, and then locally in Wyoming from a construction and operation standpoint. And so we'll talk about the siting in Wyoming in a couple slides. So more key elements of this Natrium ARDP project. Like I said, it's a pretty aggressive agreement between us and the U.S. Department of Energy. It's a 50-50 cost share. So there's strong private financial backing at about 50% of the overall project, and the U.S. government pays 50%. So we're really partners in this project with the DOE, but we have a lot of skin in the game, and the government's got a lot of skin in the game. So we feel like this is a great arrangement for us.
The ARDP, that stands for Advanced Reactor Demonstration Program. Could you tell us a little bit, if you know, about the history of that program?
I actually don't know too much of the history, Carl, so I apologize. I know that we submitted a proposal about 2 summers ago, and we found out a couple months later that we won it. Congress has been very supportive of trying to get the U.S. nuclear industry back on its feet. And so I think there was a number of different acts that implemented this.
That's a good summary. And I think that before then, the last larger scale research reactor we had in the U.S. was the EBR-2, which ran into the 90s. So that'll give, hopefully that gives our audience all the context they need. This is bringing nuclear technology into the 21st century.
Yeah, this is a significant investment in our infrastructure by the U.S. government. And so, this is really boosting this industry. And I guess the last thing I'll say is with the infrastructure bill that recently passed, we don't have to go back every year and ask for more money. The money is set for a good portion of this duration. So it really helps us have long-term security deploying this product. Once again, we have to procure a lot of important equipment. We have to construct it, then we have to start it up all within 7 years. So it's an aggressive project in that. And so not only are we trying to bring the advanced nuclear industry back into light, but we're doing it very quickly. A big part of this project is developing the HALEU metal fuel supply. HALEU stands for high assay low enriched uranium. This is a risk of our project, is getting this fuel set up and developed in time for our reactor project. And part of this is actually funding the development of 2 cascades of centrifuges that would produce this capability. So we have to design, license, and construct a fuel fabrication facility. And our partners at GEH are helping us on that. And then part of this is just the continued effort of advanced fuel and material development that has been developed for about 15 years through traveling wave reactor, and it will now continue through this Natrium project. This shows a little bit of a roadmap of where Natrium was, is, and is going. Over to the left here, the PRISM technology is what GEH has developed. Between PRISM and the traveling wave reactor, we have been developing some of this technology for quite some time. As I mentioned, we got together in what we call the pre-demo phase and kind of developed the Natrium product. And then starting with last year, April 1st, our Natrium demonstration plant project started. And then we really see an opportunity to deploy this at a fleet level throughout the US. And so we see that the next step in the Natrium program is a fleet of commercial reactors, which we're demonstrating with the demonstration reactor being deployed in the next decade. This shows an overview of all the team members. As I said earlier, when we developed the proposal, we put together a really solid team. TerraPower is shown up here on the left, and we are managing the project. Most of the main national laboratories supporting us in different ways, and this is great because we're able to leverage both expertise and testing facility at the national labs. And then we've got a number of universities that have joined their team, and they're supporting us in different facets as well. So jumping into the technology, this is what the Natrium reactor looks like. First off, this is a pool type integral reactor. So all of the primary coolant is within the reactor vessel, and all the major pieces of equipment to operate the primary circuit are within the reactor vessel. This is a really important part of our safety case. Since no primary coolant leaves the reactor, we are not susceptible to a loss of coolant accident. A loss of coolant accident is hypothesized that a piece of piping that connects major pieces of equipment, it breaks, and all your coolant leaves your reactor. Since everything's within the reactor vessel and we have no large penetrations in that reactor vessel, that major accident is no longer something we have to worry about. Since we use liquid sodium as our primary coolant, which has great heat transfer capabilities, we actually can operate our reactor near atmospheric pressure. It is only slightly pressurized to a couple PSI. This is another really great safety feature. Since it's near atmospheric pressure, this reactor vessel doesn't have pressure applied to it, whereas existing LWR reactors have 2000 PSI applied to it. That lack of primary pressure really reduces the load on our primary structures and really reduces any type of frequency of a failure of our reactor vessel, increasing our safety stance. We have a fairly large hot pool of sodium and a fairly large cold pool of sodium within our reactor. These large pools of liquid sodium provide quite a bit of thermal inertia to our reactor. So we're able to kind of ride out thermal issues because we have this large thermal inertia. On this screen, you can see this red region up here is the hot pool, and this blue region down here is the cold pool. I'm going to talk now kind of about how sodium goes through our reactor from a flow standpoint. So cold sodium, liquid sodium, and when I say cold, it's not that cold. It's about 360 degrees Celsius, so it's actually still pretty hot, but we call that cold. Cold liquid sodium, which exists in our cold pool, is sucked up through our pumps that are inside our reactor vessel. These are electromagnetic pumps as opposed to like a mechanical pump. The pump then pushes the cold sodium to the bottom of the core. Our reactor core is right here. And so cold sodium gets pushed up through our core, and inside our core is where fissioning is happening. So this is where heat is being generated through nuclear fission. The cold sodium picks up the heat from the nuclear fission reaction and brings that hot sodium up into our hot pool. So up here we have hot sodium in the upper portion of a reactor vessel. When I say hot sodium, it's about 510 degrees Celsius, so pretty hot. This hot sodium is then drawn down through these intermediate heat exchangers, and the heat is transferred from the hot sodium to an intermediate coolant system. And the intermediate coolant system comes in through these heat transport loop piping shown up here. There's another series of these pipes over here, but they're just kind of cut off. So intermediate coolant comes in and picks up that heat and then takes the heat off out of the reactor systems into our energy island. The cold sodium from our intermediate heat exchangers then goes back down to our cold pool, and that completes the primary heat transport cycle. A couple other things to note on this slide is that our control rod drive mechanisms are shown here at the top of the reactor vessel, and they control elements inside the core. So these mechanisms, which are basically motors, are able to bring control absorber bundles up and down axially within the core. That's how we control our reactivity. And then if we ever need to turn off the reactor, we basically just push the control elements down into the core. In a case of an accident, some type of event where we need to scram the reactor, we would just basically drop the absorber bundles and gravity just brings them down into the core. Two other interesting things to point out here is, one, we have a guard vessel. This guard vessel surrounds our reactor vessel. It's basically a second reactor vessel. And the whole thing the guard vessel does is, in case of a leak of our reactor vessel, which we think is not that likely, the sodium would leak out of our reactor vessel and would be contained within our guard vessel. And because it's so close to a reactor vessel, we can actually theoretically keep operating the reactor with a leaked reactor vessel. This really increases our safety stance because in case the reactor vessel does leak, we can still operate. We would more than likely shut the reactor down. We can shut the reactor down very calmly, coolly, and we don't have to like freak out about it. So this guard vessel really helps increase our safety stance and provides us a backup, which really goes a long way. One more thing to notice is our in-vessel transfer machine. We do have to shuffle and replace our fuel, which is down here in the core. The in-vessel transfer machine does remote fuel handling. Since this is liquid sodium, you can't look into it. You can't send people down into it. It makes it difficult to do things, so you have to design remote equipment. So we have an in-vessel fuel handling machine that does our remote fuel handling. We're able to shuffle fuel assemblies around. We're able to remove fuel assemblies and handle them using ex-vessel fuel handling equipment. So that is our reactor equipment. Taking a look at our site, this is our Natrium Reactor site. And this is basically what we're building in Wyoming. This is our demonstration plant will look exactly like our commercial product. So the equipment I just showed is within the reactor building shown in the middle. And all of our facilities and equipment needing to both control and operate our nuclear reactor are grouped here in the middle of the picture. And this is what we call the nuclear island. On this slide, I show an orange boundary. And this orange boundary shows the nuclear island. Outside of the nuclear island is what we call the energy island. And this is where all the equipment we need to generate electricity is. And we are actively separating our nuclear island from our energy island because we see a lot of benefits in this approach. And we call it decoupling. It's a physical separation of these areas. So I'm going to trace our heat transport from our reactor to where we generate electricity. So like I said earlier, our reactor is in our reactor building, and this is where our heat is generated. And on the last slide, I showed you that heat is removed from the reactor using our intermediate heat transport system. And so that is where the molten salt comes into play. Molten salt is our intermediate heat transport coolant, and we bring that salt in from these salt pipes that go into our reactor auxiliary building. And there's some equipment in the reactor auxiliary building that help us process the salt. And that salt is then exchanges heat with the sodium, as I previously said. And then that hot salt leaves the reactor auxiliary building and goes off to these energy storage tanks. So that hot salt leaves the nuclear island and enters the energy island. These energy storage tanks are where we do our energy storage. They are large tanks of molten salt. There's a hot tank and a cold tank. We pull cold salt from the cold tank and transfer it to the nuclear island to exchange heat. And then the hot salt comes back from the nuclear island and gets deposited in the hot salt tank. From the hot salt tank, we're able to divert hot salt to the steam generator equipment shown between these two tanks. The steam generator equipment obviously generates steam from the hot salt, and we take the steam, run it through the turbine, and generate electricity. So the equipment in the energy island is all focused on storing the heat generated from the nuclear island and generating electricity from it. Through the usage of these energy storage tanks, we're able to decouple the heat generation from the energy production because these energy storage tanks provide a buffer where we can operate these two different sites decoupled from each other. And we see a lot of economic advantage from that. Going back to the nuclear island, next to the reactor building is the fuel building. And this is where we do all of our on-site processing for fuel. So we bring new fuel assemblies in and we get them ready to go inside the reactor vessel, and then discharged fuel assemblies come out of the reactor vessel and get processed and get ready to be sent to dry storage in this building. And then we have a couple other facilities in the nuclear island, a control building where we control the reactor, and some power and electrical distribution buildings. Also shown are things like warehouses and admin buildings. We've got standby diesels and fire water protection and whatnot. But this is the Natrium project, and this is what we're going to be deploying in Wyoming and ultimately, hopefully, deploying it elsewhere as a fleet application.
I know there's a lot of implications in terms of making a different mix of isotopes or something like tritium, and what you're saying is that that's not going to be a possibility for the first Natrium reactor in Wyoming. And is there a likelihood of that?
I would say no. I mean, we're creating this reactor to generate electricity. That is our main focus. So we're not going to be doing something else with it. Yeah.
Wonderful. How many reactors could you guess are going to need to be ordered before you start to factory produce the components?
It's hard to say, mainly because everything's still kind of theoretical until we start making a lot of them. We would not be surprised if there's 4 or 5 orders coming in over the next 5 to 10 years. I think when we start thinking of nth of a kind factory type productions, we generally need to see something like 5 to 8 maybe. And so somewhere in there, that's quite a bit of increase from our current nuclear industry. Right now, we're kind of building 2 reactors in the US, and it's taken us a long time. So building these 2 new advanced reactors will be a big step up. And then if we're able to get to the point where we've got 4, 5, 6 current projects ongoing, that would be a significant boost to the supply chain.
Yeah, I'm going to put a little bit of context to that. We did have the Baraka plant built before, and in fact, lapping the U.S. plants. The Vogtle is the last U.S. project that we're building here. But then Baraka built 4. The first one, of course, took a little bit longer, and the Baraka 4 is pretty much on schedule at this point. So that's encouraging. When we talk about the speed of deployment, there's, of course, China, and China's building about 1 a month for their target of 140 reactors by 2035, I believe. So to give it a sense of scale, if 3 natriums are like 1 conventional reactor, then we would need to start about 9 natriums every month in order to match China's progress for the rest of the world. And I don't know about anyone else out there, but I'm happy to see that take off.
Well, let's walk before we run, but yeah, sure. Once we get to deploying multiple Natrium products in hopefully the near future, we will have to switch to a Part 51 licensing scheme where we have a standard license. And so that's something that we'll have to do in the future.
Great.
I stole this slide from Nick Turan, and after putting it on here, I realized that these pictures might not be 100% right. But so on the left, you see what I thought was a picture of liquid sodium, but when I read it, it's actually mercury, but they look very similar. So that's what a liquid sodium would look like. It's a liquid metal. On the right is a kind of a graphic of what molten salt looks like. What is shown here is FLIBE, which is a very expensive molten salt. And on Natrium, we're actually deploying just regular solar molten salt. So that is a different chemical makeup. And so it's a kind of a less corrosive, easier to use salt.
And so the sodium salt, that would be something that's currently deployed at Ivanpah right now.
Yeah, there's Ivanpah, there's Solana, which are 2 US-based concentrated solar plants. There's a lot in South America and Spain, deployment of a concentrated solar plant, which uses these solar salts pretty commonly. It's actually, the salt we use is something you can go buy from a chemical company. It's pretty much a common material, and we're using it at like just industrial concentrations. So from a technology development standpoint, it is deployed and demonstrated, and it's nothing we have to do any R&D on. EBR-2 was a sodium fast reactor that was built and operated at Idaho. The fast flux test facility was a sodium fast reactor built and operated at Hannaford. And so these are 2 reactors which we rely on quite a bit from lessons learned. The liquid sodium we do use in a reactor is a fairly high purity level, so we constantly have to purify it using a sodium purification process. A lot of that stuff has been figured out at both EBR-2 and FFTF, and we are standing on the shoulders of those giants to make sure that we've got good technical basis for operating our reactor. There's companies that sell the sodium, but we need a lot of it. So actually just buying the sodium and getting it ready to fill your reactor is a whole logistics problem, which is kind of interesting to go off and solve. But the molten salt's actually easier to buy and melt and put in your tanks. So it's kind of interesting. Again, on the next slide, this actually shows the inside of our reactor facilities. In the middle is the reactor building. So this was kind of in the middle of the plot plan picture before. One important thing to note here is all of our kind of critical reactor systems are actually subgrade. And this gives us quite a bit of protection from any types of external accidents. Our reactor is subgrade, and you can see this here. This is what I showed in a couple slides ago. A reactor core is down here. These are the intermediate piping that I talked about in the past, and then that goes through some what I'll call processing equipment and then leaves through the thermal storage. Above the reactor is kind of a refueling area. So when we have to either insert or remove fuel from the reactor, there's equipment that comes over this area and then interfaces with the reactor. And then it takes the equipment over to our fuel handling building. And once again, I showed this in the plot plan, it was kind of to the lower right. We're able to process new fuel, process spent fuel, and then we kind of store some spent fuel in a water pool similar to LWRs for some amount of time before we put them in dry casks and put them out on storage. But our fuel pool and our reactor and some key parts of our processing equipment are all subgrade. So in a case of something like an airplane accident or a tornado, all this stuff is protected because it's below ground and reinforced with some beefy concrete. And this really helps protect our safety stance. And then everything above ground, there's no safety related equipment above ground. And so they can be built relatively inexpensively since they don't protect any safety related equipment. They can just be constructed out of steel. One other important thing to highlight here is that the way we remove decay heat in an accident scenario is through a system called reactor auxiliary cooling. And it acts off of natural draft circulation using air from the outside. It's really pretty cool. So air from the outside gets drawn down into this cavity around the reactor using these ducts. And so you'd see 4 ducts here. 2 of them are for cold air. So air gets drawn down to this reactor cavity. It makes a right-hand turn underneath the reactor and goes up through an annulus between the reactor and the support column. And that air actually can remove heat from the reactor vessel. And then that hot air leaves the reactor building through another set of ducts. This system is always on. There's no blowers, there's no vents. It is just always open, it's always active. So in a case of an accident where we lose the piping to our thermal storage tanks or how we normally remove heat, this system will start removing heat at higher and higher rates the hotter it gets because it acts off radiative heat transfer. So the hotter this stuff gets, the more heat it removes, and it just can remove enough heat to stabilize the reactor in case of a really severe unprotected accident. Since there's nothing that the operator has to do to activate this safety system, it's really robust and there's really very few failure mechanisms associated with them. So it's a really cool, simple, robust safety system which we implement. And if anyone studied an LWR, they've got all these emergency core cooling systems, which are all pressurized pipes that have to get water down to the core. We don't have anything that, we just have some open air ducts that work.
And since we're on that topic, is there a change in reactivity if you exceed your operating temperature? Is that a safety measure?
Yeah, so there's a temperature reactivity coefficient. I think that's what you're referring to. As temperature goes up, in general, reactivity goes down. There's an inherent self-balancing behavior of the core. There's a number of different specific reactivity coefficients that kind of all work together. And so, yeah, this was actually demonstrated at EBR2, where they were able to kind of not scram the reactor, insert some reactivity, and the reactor actually self-corrected and came down to a stable state. And so our reactor has the same thing, and there's other reactivity coefficients that when you add them all together in a time-dependent thermal and power-based analysis, we can demonstrate that our reactor kind of always reverts to a stable state, which makes it very safe. So that kind of ends the discussion of what the reactor is. I'm going to get a little bit into load following and this energy storage concept, which we think is really valuable as a product in the US. One thing that we just recognized talking with utilities is they all kind of have these really big plans for rolling out renewables. Based on all these zero net carbon initiatives, they have to deploy renewables, but renewables don't produce energy throughout the day. And so the utilities are looking for zero carbon flexible energy products other than renewables to help offset this renewable energy issue. Nuclear reactors can be that solution, and we feel strongly that they are part of that solution. LWRs can load follow, and by load follow, I mean change their power output throughout the day. That's what load following is. And in Europe, they're actually kind of required to do load following. They have fairly slow ramp rates, so 5% power per minute. And when you do load follow with a standard reactor, your capacity factor goes down, and that's linked to your economics. So by load following, you're kind of reducing the economics if you're turning your reactor down. This plot on the right kind of shows what's sometimes referred to as a duck curve, where kind of in the middle of the day, you have an excess of electricity, and then during these other portions of the day, you have more demand. And so this shows kind of the time-dependent need versus supply that a lot of people who are trying to solve this problem are focused on. But we are deploying load following through this energy storage system, which is decoupled from a reactor. So a reactor can always run 100% power, and then we can flex the electricity output generation through the energy storage system. And the size of these thermal storage tanks allow us to save up to 5 to 6 hours of electricity, not produce it, and then produce it all at once. And so we're able to oversize our turbine generator compared to a reactor, and then basically store up energy and then output it at a higher rate. And doing this way, we're able to actually make more money. And then we're also able to couple with renewables, because when the sun's out, solar's making energy, we can not create electricity, store up the energy we're making, and then sell the electricity when the sun goes down, basically is the concept. How do we do this? It's actually taking advantage of concentrated solar plant energy storage systems. So the concentrated solar plant industry has already implemented large-scale energy storage as part of their product. Left here is the Solana generating station in Arizona. They've got 6 tank pairs of energy storage. They use solar salt. They store the heat in these tanks, and then they send the salt from these tanks, their steam generators, create electricity, and all that equipment is shown here. So already deployed, already proven to work at a commercial scale. We are basically borrowing that technology and applying it to our sodium fast reactor. So our version of this technology is shown to the right. One of the nice things we can do with the Natrium technology is, since we've decoupled the nuclear island from the energy island, is we can start talking with utilities and really tailor the energy storage and the turbine sizes to each utility's needs. So every 2 years, the utility does an integrated resource plan exercise. They figure out what their future energy needs are. We can give them higher flexibility or more variables to our product than other products. And so using this energy storage system and providing flexibility is really advantageous for our deploying Natrium as a fleet product. So we could change the number of tanks, we could change the size of the tanks, we could change the size of the turbine, all based on the customer's need. For the Wyoming site, we're doing 2 energy storage tanks, 1 tank pair. We're doing a 500 megawatt electric turbine, creates an equivalent of 345 megawatt electric. So we're oversizing the turbine by about 50% or so. This is a cool plot put together by partners at GAH. This just kind of shows, is a little bit more of an active plot of how we would operate the energy storage. So in the middle here, you see a day's use of electricity at CAISO. CAISO is the California market. You could see 2 distinct peaks, one in the morning, one in the evening, and then a really low part during the middle of the day. So you're seeing here is the penetration of solar into their grid energy usage. In the middle here, you could see what the Natrium turbine would be doing during the portions of the day to the left. And then on the right, you could see what the Natrium storage tanks would be doing. Simply, when the electricity price is low, you could see the power is down and our hot tank volumes are increasing. When the price is high, you could see our power output is high and our hot tank volume is decreasing. So once again, storing when the price is low, deploying when the price is high. And we see a fairly decent rate of return by operating this equipment this way. So that kind of concludes the load following, price following talk, and we're really excited about that portion of our technology. I'm going to talk a little bit about fuel, and then we're going to get into licensing, and then we'll kind of wrap up. So Natrium fuel, we are advancing kind of the state of the art of the metallic fuel from what it has been operated in the past to kind of a new type of fuel. We are using a uranium zirconium mix. Traditionally, they've used a uranium zirconium mix. We are trying to change that fuel technology quite a bit. Traditionally, they would bond the metal fuel to the cladding with a sodium bond. We are trying to remove that sodium and use a mechanical bond. The fuel slug was cylindrical, and we're going with an annular fuel slug. Of these technologies allows us to get to really high burnups per fuel, which really creates an economic competitive advantage and actually makes this sodium fast reactor technology competitive with other energy sources. So we're able to really significantly increase the lifetimes of our fuel. TerraPower has been developing fuel for a while now. Like I said earlier, I think what it says here since 2009, so that's about 13 years. We have worked with vendors on developing manufacturing capabilities of our fuel cladding, which is a kind of a specific type of stainless steel called HT9. And we've done a decent amount of variation testing, both in the ATR, which is at INL, and at Bor 60, which is in Russia. And so we've sent both our fuel and our cladding different areas to different test reactors to get testing information done so that we are confident that it will work. We've actually covered a lot of the safety strategy, so I might go quickly through this. I will point out there's three key elements to safety for a nuclear reactor. It's control, cool, and contain. You basically need to control the reaction, you need to cool the reactor, and you need to contain the products, the radionuclides. So all safety strategies kind of start with those three words. We call them the 3 Cs. So, how do we control the reactor? As I mentioned earlier, we've got control drive lines that are connected to control absorber bundles, which are in the core. If something happens, we can scram the reactor. We basically release the absorber bundle, and that's kind of shown here. And that inserts in the reactor. That's based on gravity. If for some reason that doesn't work, we do generally deploy a motor runback of these mechanisms. Means after we scram, we run the motor all the way down to kind of force the control rod into the reactor. So that's a common practice. Another important point is in our sodium fast reactor, based on kind of the neutronics of the core, we only really need to put 2 of our control elements into the core to shut it down. And we've got 13. And so from kind of a backup standpoint, a bunch of stuff can go wrong and we could still shut down the reactor. This is a little bit different than the LWR world, where they have to insert all but 1 to turn off the reactor. All we need to do is put in 2. So it kind of adds to the robust safety case of our reactor design. And then the last point is that we do have an inherent feedback behavior of our core that can return the reactor to a stable state after some unprotected extreme event. That's our safety case surrounding control. So these are the plots that we were talking about earlier, where if you have some significant reactivity insertion, the core will go up in power until the temperature and power coefficients really start taking over, and then it'll return to a very stable state. And even though we might get some localized fuel cladding temperature increases, the fuel itself always stays well below melting point, which is, you're really worried about melting fuel. And we've got hundreds of degrees Celsius margin between our melting limit and the actual performance of our fuel during really some extreme accident scenarios. So here we've got a number of ways that we kind of cool the reactor core. Under normal operations, we're actually taking that heat off and dumping it in the storage tank. So that's normal operations, that's how we generate electricity. We do have a heat removal system on our intermediate loop that can directly remove heat. We take advantage of this from an operation standpoint. When you start up and shut down the reactor, it's nice to have a nice locally controlled heat removal equipment. So that is on our intermediate system, and it's called our intermediate air cooling system. But all of our safety-related decay heat removal systems is this RAC system I talked about earlier, the reactor air cooling. That is always on, and it's really just a natural draft flow, no operator action. So very robust and something we can always count on. And this graphic kind of shows the air path of this RAC system, how it comes in from the outside through the ducting, goes down to the reactor cavity, comes up around the reactor vessel, and then leaves the reactor vessel. Containment, this is how we contain stuff, is through a containment strategy. And so we've got a number of barriers for containment. Once again, our primary systems are low pressure, as I mentioned earlier. So there isn't a pressurized reactor vessel that might break. It's low pressure, so the probability of the reactor vessel itself failing is very low. The primary system's all within a reactor vessel, so we're not circulating coolant outside of our reactor vessel, which helps our containment story. We do put an intermediate coolant into our reactor, but that intermediate coolant is a closed loop, so we're able to turn that off if something happens. There's a high compatibility between our fuel and the sodium itself, and so if there is an issue with our fuel, the sodium itself really likes to hold on to a lot of the radionuclides, so what you're trying to contain kind of remains in the sodium. We do have a containment strategy that relies on multiple barriers for containment. And as I said, the fuel, the reactor vessel, and the structures immediately surrounding the reactor vessel are all play a role in these multiple functional barriers for containment. So that kind of wraps up the safety strategy.
If there's a leak in that vessel, is there a risk of a fire, and is there a strategy for preventing that?
It's a great question. So once again, sodium is our main coolant in the reactor. So in the case of a sodium leak, first of all, where is the leak coming from? There's probably a couple places where sodium can be leaking. Once again, it can leak out of the reactor vessel. And so we have a guard vessel that protects any leaks out of the reactor vessel. There's an annulus between the reactor vessel and the guard vessel, and that is an inerted space. So that is inerted with argon, which is inert gas. Sodium doesn't catch fire if it's an inerted environment. So if sodium was to leak out of the reactor vessel. It would go in the space between the guard vessel and the reactor vessel. It would not catch fire because there's no air or water in there to catch fire. It would go into the catch pan, and the catch pan would basically snuff out the fire, the reaction, because there would not be any air to fuel the reaction. And so from a design philosophy standpoint, any piping that contains sodium that leaves our reactor generally has a guard pipe around it, and the guard space between the guard pipe and the normal pipe is inerted. There are a couple areas in our reactor where we need sodium for other reasons. They are generally either in an inerted environment or have guard piping or have what we call catch pans below them. And the catch pan is an engineered feature of a piping area where if sodium was to leak out, it would go into the catch pan, and the catch pan would basically snuff out the fire, the reaction, because there would not be any air to fuel the reaction. Another thing to note is sodium fires if sodium interacts with water. As I've noted, our steam generators, where there's pressurized water on one side, which turns into steam, actually interact with our salt and not our sodium. So we've actually removed the whole issue of water to sodium interactions. And based on the concentrated solar plant industry, we know that salt and water do not have a reaction that we have to worry about because they actually have leaks in their steam generators and they keep operating. So that is not an energetic release. There's actually a little bit of water in the salt when you get it. Anyway, it burns off when you heat it up to the temperatures we're working out, but salt and water mix in general.
Is there any kind of corrosion problem with the sodium? Is there any kind of embrittlement problem that you're going to have to address with the reactor or the piping?
Yeah, so sodium doesn't have corrosion issues. It actually works with stainless steel really well. All of our steel that hits sodium is stainless steel. We have different varieties, but it's very compatible with stainless steel. I hear stories from other sodium fast reactors where after they drain the sodium, they still see the fabrication marks on the reactor vessel. So if anything, it cleans up the sodium. Anything that's left on the steel actually will get into the sodium. You have to clean the sodium more so than the sodium affects the steel. So very little corrosion concerns. At very high speeds, there's some erosion concerns, but we generally design for that. We make sure there aren't local high velocities on all of our flow channels. So the solar salt we use does have corrosion issues. Some steam generators, heat exchangers that see the solar salt will have to be designed with corrosion allowances, which is common practice once again in the solar industry. All the heat exchangers and steam generators that see the salt are replaceable and maintenanceable. And so if we do have corrosion, we A, try to design for it, and B, we can replace or maintain that equipment. Licensing strategy, like we talked about before, we're doing a 10 CFR 50 licensing process, and that was really due to the time requirements. It's a two-part process. We submit an environmental report and a construction permit, and the construction permit application includes a preliminary safety analysis report. That goes off to the NRC for review. We're doing lots of engagements with the NRC. We're engaging with them right now officially. We're doing presentations. We're providing topical reports. So there's a lot of interaction before this first application. And the whole reason for that early engagement is really to get out in front of any key issues that we might think they have. So generally, this shouldn't be the first time they're seeing anything because we should have already told them something ahead of time. But right now, we're meeting with them every couple of weeks, talking through different topical issues and really teaching them about our reactor design because they are not necessarily experts on our technology, but we need them to become very knowledgeable about our technology very soon. So a lot of this is actually education for them. So we submit the construction permit application. Hopefully that's about a 2-year turnaround before they approve it. And then a couple of years later, we submit an application for operations, and that will include our final safety analysis report. Okay, so these are the dates. So our CPA will be submitted August of next year, which seems like really close. We're working aggressively towards getting that submitted next year. It's about a little less than a 2-year turnaround, hopefully. And the NRC has communicated with us that they think this is doable. But we would receive the license to construct March 31st, 2025. After you submit your PSAR, you kind of continue to design and work on your reactor, and then our operating license application and our FSAR would be submitted the following year, and then hopefully a 2-year turnaround on that, and we would receive our license to operate March 31st, 2028. And that is basically Congress decided that they wanted to see these projects deployed in that timing window, so we are complying. So these are pretty aggressive dates. And then lastly, where are we building it? We went through a pretty decent site selection process. There's a lot of stuff that goes into site selection. It's a whole process: seismic activity, volcanic activity, flooding, historical artifacts, endangered species, water access rights. The ability to actually transmit the power to the population that needs it is huge. Excavation, you want a relatively flat site. Accessibility for just receiving some of the large components we need. Can we actually get things shipped to the site? And then some kind of other things you don't really think about, but like construction staff, operating staff, where did the people actually come from that work on this plant? And then lastly, but probably most importantly, do these local communities want the plant? Because certainly if there's local opposition, it's going to make it really hard to go forward. PacifiCorp, who's got a number of generating facilities in the West, kind of focuses us in on Wyoming. And they actually had 4 different sites where they were decommissioning coal plants in the near term. And we have always thought that kind of the coal plant industry winding down and turning off their coal plants is a great opportunity for us to step in and take over a coal site and replace that lost coal generation with nuclear power. We've actually kind of, from a market standpoint, studied coal plant retirements and tried to size our reactor to be able to get into that market. And so out of these 4 sites in Wyoming, we chose the Naughton site, which is in Kemmerer, Wyoming. And you can kind of see the location right here in the bottom left corner of Wyoming. It's fairly close to Salt Lake City, a couple-hour drive. I think this is kind of the end of my slide deck. This is kind of our takeaway slide, dispatchable power. And we eventually think there's a need for process heat and those energy storage tanks we can use for process heat on top of electricity generation. And we are leveraging kind of some of the construction techniques learned from the combined cycle gas turbine industry. That industry is able to deploy their technology very quickly. And I think that's it. Appreciate the opportunity to share with this group. Yeah, and any questions, feel free to ask.
There was a question about if the cylinders got swollen, and in fact, you talk about the thermal properties where the expansion of the core and the nature of the refueling rods and the control rods are such that they slide in easier with thermal expansion?
It's a little bit different than the LWR community. We have discrete control assemblies. So they're fairly robust from a deployable standpoint. Like I said, you only need 2 out of 13 to go in, and those 13 are distributed throughout the core. So the thermal expansions that I'm talking about that control the reactivity of the core are on the orders of magnitudes of millimeters, actually. If the whole core breathes 1 millimeter, you insert quite a bit of negative reactivity. Those control rod ducts and the control rods have a lot more than 1 millimeter gap in them. So if the whole reactor was expanded a couple of millimeters, you would still have enough margin in the geometric features that you could insert all your control rods. Hopefully that answers the question.
Yeah, wonderful. So what do you think the highest operating temperature? I saw, you mentioned 510 degree outlet. Someone else said we thought it was 540 outlet. What's the variation there?
Yeah, so we can get up to 540, 550. So I probably use lower temperature than our capabilities. We could certainly get a lot higher. There's trade-offs on the fuel. So fuel lifetime is limited based on a number of things. One of the things is how much it swells, which is usually limiting. And there's a temperature dependence there. So our more advanced fuels that I talked about can operate at higher temperatures. They have longer lives at higher temperatures. Some of our earlier versions of that fuel form might have shorter lifetimes at higher temperatures. So we might operate them at lower temperatures until we get it fully qualified. But we'll probably start up at 510, make sure everything works, and eventually transition to a higher 540 temperature. And so that temperature is limited based on fuel performance. The sodium itself boils at it's 800 or 900 degrees Celsius. So the boiling point of sodium is really, really high. One thing you're always worried about with your primary reactor coolant is when does it boil and your margin to boil. We are always very far away from boiling because the boiling temperature of sodium is so high. That usually is not a concern for us. As opposed to in a BWR, you're already boiling water. So it's a little different.
And so with those great higher temperatures in the future, I'm assuming that making hydrogen H2 for fuel use for conventional process and automotive and et cetera will be part of the possible product.
Yeah. So yeah, I didn't touch on this too much, but it's a great point, Carl. These energy storage tanks, right now we're diverting the heat to make electricity, but in a future world, we can divert the heat to make hydrogen. We could divert the heat to make concrete. We can do whatever you want with the heat. So we really see this energy storage system being part of an integrated energy system that in the future, users could build a station next to our energy storage tanks and use the heat from the salt for whatever they want to use it for. And I don't think this is too far away. With all these green energy initiatives currently at the utilities, eventually they're going to get rolled down to the industry, and people who are using dirtier forms of energy are going to have to figure out how to clean up their energy source. And this integrated energy system is going to start being an option there. So whether it's hydrogen, whether it's concrete, whether it's a refinery, there's opportunities here to kind of deploy this technology across the board from a process heat standpoint.
And just to cover some of these easy questions, someone else is asking about the molten chloride reactor. I know that's a separate group from yours.
Yeah, I didn't mention the molten chloride fast reactor project at TerraPower, but it stemmed out of the traveling wave reactor concept. They have a molten fuel, so the fuel is dissolved in their molten chloride salt, and they're able to get to this breed and burn cycle with liquid fuel, which is really pretty cool. And it is a really cool technology. They have a lot of development to do, but it's actually really pretty neat. And our laboratory up in Everett has quite a bit of scale testing going on to try to develop this technology. So it is a really cool project. It is a different reactor project at TerraPower. We do share a lot of the same resources and a lot of the ideas, though. So we're pretty integrated.
And so is the Natrium Reactor product line able to work with spent fuel, or will it only be a different product?
Kind of on my roadmap that I showed, the Natrium product line will run off of a HALEU fuel form, so it will not run off spent fuel. So something in the future down the product line to the right, and future generations would have to handle that. And the kind of the traveling wave reactor concept of breeding up from like a depleted uranium source into this U-239 fissionable product is based on that. That would become later. You know, like I mentioned, we really have to prove out our advanced fuel form, its robustness and its long-lived capabilities, and then we can transition to that kind of technology. That would be Natrium 2.0, if you will. Maybe it's 3.0.
Very cool. So do we have a sense of the cost profile of the Natrium product line and what these economies of scale are going to give us once you get that nth of a kind reactor?
I would say yes. Everyone kind of holds them tight to the chest, so I probably won't communicate too much in numbers. And they're all, I'll say, somewhat meaningless until you actually build one. We're still in the design phase. We think that it will be competitive in today's market and definitely in tomorrow's market, where low carbon energy technologies will be sought after.
Okay, so here's a good one. There are complaints about the fuel composition, that it's not actually producing less waste per kilowatt. Is your burnup the same as other, I guess these are HALEU reactors, so is it really as bad as LWRs, or is it much better than an LWR?
I think when you normalize our spent fuel per weight of heavy metal and kilowatt produced, our advanced fuel form, our long-lived fuel form from a uranium utilization standpoint will be better than the current LWR fleet, even though we do need to use HALEU fuel and they do not. But we get a lot more out of our fuel. And the fast neutron spectrum is really how we get there. And so the thing that TerraPower has brought to the table is this really long-lived fuel. But since we're able to push it so far based on the technology development we've deployed over the last 13 years, we're able to really turn this reactor into an economic reactor.
And how often are you looking at refueling?
Yeah, so our refueling cycles initially would be about a year, but we'll eventually get to 2 years. And once again, this is part of just the demonstration process.
There's a few questions about the flexing of your capacity, like just how much molten salt are you maintaining? I know that we have like 5 hours of about 150 megawatts. What is that like? Do you have any sense of weight or volume that you can give us?
Okay, so the tanks are like 120 feet in diameter and 40 feet tall. So someone could do the math on what the volumes are.
If you bottom out with your power and you have to power down, what's sort of the minimum power before you get into complications?
So first of all, we kind of always reserve a heel at the bottom of the tank so we don't ever run out of sodium. We're monitoring the volumes of the sodium, and they are depleting quickly, but they're not depleting so quickly that we can't respond to things. So if we're monitoring the depletion of the cold tank, and if for some reason we're running out, we have designed extra that we have some margin, but you would turn up your steam generators and you would draw more from your hot tank and then you would deposit more in your cold tank, and that's how you get out of it. If you are really upside down, you would just turn off the reactor. And once again, you're monitoring these rates constantly. So like you could scram the reactor, it takes seconds. And so you're definitely more than a couple seconds away from something bad happening because of this excess reserve in the bottom of our tanks. When we do transient-based analysis, we're generally like 15 to 20 minutes away from anything that happens. So like a common accident in the industry is like your turbine goes down, your turbine trips. Reactors, LWRs with a tightly coupled energy island don't have minutes. They have seconds at best to respond to that. We've got like 15 or 20 minutes. So we could trip our turbine, not do anything for 15 or 20 minutes, and then shut down the reactor if we had to.
Oh, very good. And is there a single turbine, or can you do deeper throttling with multiple turbines? And is that the situation you're in?
Right now, we're just speccing out one turbine. I will say there's probably room for innovation or improvements in the turbine design. Right now, we're just leveraging what the concentrated solar plant does for a single tank pair. The Solana plant that I showed earlier actually has multiple turbines.
Is there a scenario where you're going to have to go into the reactor vessel, or is it sort of the plant is basically decommissioned at that point?
You never want to go into the reactor vessel, so I would say no. I would say all of the key equipment that lives in the reactor vessel is replaceable from outside the reactor vessel. So we have maintenance equipment that attaches to the reactor vessel, inerts the cask environment, and then can go down and remotely remove a piece of equipment and plug the reactor vessel, and then we could bring a new piece of equipment and put it in the same way. If we had to get down in there and replace structure, that is where we probably can't do it. We can't drain the sodium and fill it back up, if you know what I mean. So yeah, if we found out like the bottom of the reactor vessel needed repair, that'd be a really bad day at the plant, and that'd be a difficult thing to recover from. But I gotta believe that is true of most reactors, to tell you the truth.
This is the standard question for any nuclear plant. What about tangential threats from bad actors? So is there anything different in the Natrium product?
One, we have a lot less safety systems. And so like I mentioned, a reactor is inherently safe. And so the amount of stuff a bad actor could come in and monkey with is really reduced. So we have some natural protection there. I did mention that all the safety systems and systems that are important to radionuclides are below grade. So if you're bringing something in from outside, like an airplane, it's naturally protected.
So thanks so much for hanging in there. Thanks, everyone.